Hello. In this video, I want to go over some popular probability problems to recap what we did in this chapter. Let's get started. So the first question I want to talk about is a rolling of a dice question. So it says a fair six-sided die is rolled once, and then it asks us to find the probability of three different scenarios. So remember, if you're rolling a die one time, you have six sides, 1 through 6 on your die. So you have 1, 2, 3, 4, 5, 6. And from that perspective, let's see if we can analyze the first question. What would be the probability of rolling a number which is greater than 4? So you have to think through what are your options here. Greater than 4 on a die would be a 5 or a 6. That means there's two ways that we could do this. Remember that probability was the number of favorable outcomes over the total number of possible outcomes. So 2 favorable outcomes out of the total of 6 possible outcomes reduces down to 1/3 as a fraction. Again, you could always convert this to a decimal percent. Let's do the next one. What's the probability of rolling an even number? This one you should know by heart, right? Because half of these numbers are even. So the answer is 1/2, but you could have worked it out the long way. 2, 4, and 6 are your 3 even numbers. 3 favorable outcomes out of the total 6 possibilities, which does reduce to 1/2 or 50%. It would have been the same if I had said, what's the probability of rolling an odd number? Now the next one can be a little tricky. I encourage you to pause the video and try it yourself. It says find the probability of rolling an even number or a number greater than 5. Okay, so notice that word or here. We did talk about the probability of or, the probability of A or B. Remember that formula, what we said to do? Or meant to add, that's right. So we would take the probability of the first A plus the probability of the second B minus the probability of both occurring. So any overlap, if you will. So in this case, the probability of A is the probability of getting an even number. B would be a number greater than 5. So what numbers are greater than 5 on a die? Just a 6. The probability of rolling a 6 minus the probability of both, assuming that it's possible to get an even, which is also 6. So in this situation, we'd say, well, to get an even number, that would be 3 out of 6. To roll a 6, that would just be one way to do so out of 6. But have we repeated anything, right? Is it possible, in other words, to have already talked about a 6 when we talked about the even numbers? Well, yeah, because one of those even numbers was a 6, right? So we have to subtract both the one that is in both categories, the overlap, if you will, from the Venn diagram type of thinking. So when we do that, we end up just negating the addition there, and we're just left with 1/2. 3 6 is 1/2, right? So in other words, by saying I need to get an even number or I need to get a number greater than 5, maybe in order to win the game, whatever it is you're playing, it's the same probability. It's 1/2 in this case, because that second option was absorbed in the first, okay? All right, let's head over to another common problem that you might see as you close out this chapter. It says that we have 2 fair six-sided dice which are being rolled, okay? So it doesn't tell us here if they're simultaneous, like do I have 2 of these die and I'm rolling them together, or am I doing one followed by another? But keep in mind that even if you were to roll them separately, these would be considered independent events because each die does not impact the other one, right? That's very different than picking a card and then picking another card from a deck of cards. Those would be dependent. Okay, so with that in mind, if we have 2 fair six-sided dice that we're rolling, find the probability that both of these numbers are greater than 5. Okay, so remember, when we're doing multiple events, what do we normally do? That's right, we multiply their probabilities. So we're saying we're finding the probability that the first number is greater than 5. Well, if you're greater than 5, then that would be a 6, wouldn't it? Okay, and means multiply. We want the probability that the second number that you roll is also greater than 5, which would be a 6. And so in order to do that, we know that there's only one way to get it to roll a 6 when you're rolling one die. So that's 1 out of 6 options. And another one way to roll a 6 on your second die, 1 out of 6 options, which ends up giving us 1 out of 36, which you're welcome to convert to a decimal and a percent if you prefer using your calculator. Okay. So again, I was multiplying because I had multiple events. And the same thing would hold if I had 3 die or 4 die. If I kept doing the same thing, I'd multiply each probability together, checking whether or not they impact one another. But these were independent events, so no need to worry about changing denominators or anything like this. Take a look at the second one. Maybe try it on your own. It says find the probability that the first roll is an odd number and the second is an even number. Does that really make much difference? Well, let's take a look. To be an odd number would mean you'd be the numbers 1, 3, or 5. So there's 3 ways to do that. That's 3 out of 6. That's the first probability. So we're multiplying each probability together, but changing the denominators or numerators if we have dependent events. But remember, rolling dice, even if they're rolled together or separate, they don't impact one another. So let's multiply by the second probability, which was the second number is even. Well, which even numbers are on a die? That's right, a 2, a 4, or a 6. So that would be 3 options again, 3 out of 6. Now you may be wondering, before you go to your calculators, right? You may be wondering if you need to reduce first, right? Could you make this 1/2 times 1/2? Yeah, in fact, that would make your math a little bit easier if you're not using a calculator, right? So this would just become 1 times 1 for your numerator, which is 1, and 2 times 2 for your denominator, which is 4, 1/4, or 25%. Okay, again, you could have also done 3 times 3 for your numerator, got 9, and 6 times 6 for your denominator, and got 36. But doesn't 9 over 36 also reduce to 1 over 4? Yeah, same thing. So in this case, it was again a simple multiplication question because you were multiplying the probability of each repeated event happening as you do more than one event after another. The last one, try it on your own. What is the probability that neither of your two dice, I should say, is a number greater than 4? Now this one is really a reading comprehension question, so let's see if you interpreted it correctly. Neither one is a number greater than 4. Well, to be a number greater than 4 would be a 5 or a 6, right? Those would be numbers which are greater than 4, okay? If I had said greater than or equal to 4, then it would have included 4. Or if I had said at least 4, it would have included 4. But it says strictly greater than 4, so that would be a 5 or a 6. But it says neither one is one of those numbers. So that means not a 5, not a 6. Well, who does that leave us with? A 1, a 2, a 3, or a 4. How many options are there? That's right, 4 choices. So you have 4 choices for the first roll out of how many choices? 6. And we multiply that by our second roll. Now for our second roll, remember the first roll does not impact the second roll of a die. They're separate events, independent events. So this would still be 4 out of 6. And just like our last question, you are welcome to reduce early to save yourself bigger numbers, right? That's 2 over 3, isn't it? Times 2 over 3 when I reduce. So I'm just left with 2 times 2, or 4, for my numerator, 3 times 3, or 9, for my denominator, which again, you could easily convert using a calculator into a decimal and a percent if needed. Okay, so now we've shown you a couple of examples that are pretty common using one die or multiple dice, I should say. Let's head to our next question. All right, so we move away now from dice, and let's talk about what happens when we're picking cards out of a standard deck of cards. So here I have my standard 52 card deck, and remember you can look those up on the internet, you can play with them yourself to try to get more comfortable with your different suits and to know what cards are in this deck. But it asks me now to find the probability that when I pick one card, it says a card is drawn at random. When I pick one card, what is the probability that it is either a black card or a face card? So we're picking how many cards? That's really important. A card, okay? That's 1, okay? If it said multiple cards are drawn in succession, then they would impact each other. Every time you pick a new card, there are fewer cards left in the deck, meaning that your denominators would be changing, as would the totals in each suit. All right, so with that in mind, let's see if we can remember how to do this. Drawing a black or drawing a face card. So to draw a black card, we would need to know how many black cards there are in a deck of 52. Remember, for a standard deck of 52 cards, you have 4 suits, 13 cards are in each suit, half of them are black, half of them are red. So this means that there are 26 which are black, and there are 26 which are red. Okay, so if you know that, then drawing a black card would have what probability? Well, it would be 26 out of 52. But even easier, you can reduce that down to 1 out of 2, right? You have half the time you're likely to get a black card, half the time you're likely to get a red card, okay? Now we have the word or. We're only drawing one card, so we're not doing multiple events, we're not multiplying, we are adding, that's right. So or means add, but subtract the overlap, okay? Face cards, another word for face card is picture cards. Remember which face cards that we have in a deck of cards? For face cards, so for face cards, you can either be a jack, you can be a queen, or a king. We don't consider aces to be face cards, right? They're either 1s or 11s, depending on what game you're playing. All right, so jack, queen, king, and there are 4 suits, and each of the 4 suits has a jack, has a queen, has a king, so this is times 4. So 3 times 4 is 12. That's right. So there are 12 face cards in your standard 52 card deck out of 52. Now, why would you prefer to maybe not reduce here? Well, if you don't see the reduction right away from 12 over 52 to what that would reduce to, it might be easier for some of you to just keep the denominators the same if you're not using technology, because you remember that you can add two fractions if they have the same denominator, right? So that would just be 26 plus 12, or 38 out of 52, right? And at this point, you can notice, I say yes, that we had one more step to do, okay? Why can I not leave the answer as 38 out of 52? Why do I have to do an extra step here? We said it earlier, but can you remember? You can check your notes. That's right, because it is possible to be a black card and a face card at the same time. In other words, it is possible to be both a black card and a face card. How many of your face cards, for example, would be black, and how many of them would have been red? Wouldn't half of them be black and half be red, right? So of these 12 face cards, you would have 6 which are black, and you would have 6 which are red, okay? So we need to subtract here. So subtract the 6 out of 52 probability, and that would take care of the overlap, meaning our final answer should be, right, we did it this way here, so you can follow what we did. Our final answer should end up being 32 out of 52. Now we can also reduce from there, can't we? Because we noticed that 32 is divisible by 4. It's also divisible by 8, right? So 4 times 8 is 32. And 52 is also divisible by 4. Remember, there's 4 suits of 13. So we would say there's 13 as my denominator. When I divide each of them by 4 here, we get 8 out of 13 as our fraction, okay? And again, you can convert this to a decimal and a percent using technology if needed. So I wanted to remind you here why I didn't multiply. Because I did not do multiple things, right? I wasn't saying I'm going to draw one card and then another card and then another card. Multiple events, we multiply their probabilities, right? And we always check if they're dependent. In this case, they would be. This time, we had one event, and we said, what's the likelihood it's this or this? In that case, we add the different options, but we subtract if we overcounted, meaning if there was any overlap, if they both could happen. And sometimes that both is not a possibility, but this time it was possible. In fact, it happened 6 times. Okay, let's head over to another question. It's a little bit more complicated. Here we go. This time we're told that a fair coin, so we have a coin which has a heads and a tails. We're going to toss this coin, and we're also going to take a fair 6-sided die and roll this die, okay? So we're going to do both of those events. Now maybe they're simultaneously done by 2 different people or someone who's very talented with both hands at the same time, not me, okay? But what we're going to do is keep track of all the possibilities. And that is called, if you remember in your notes, the sample space, right? The sample space when you perform an experiment with multiple occurrences. Okay, so once we have our sample space, we have then listed all possible outcomes. So if you remember from your notes or previous videos, we talked about the fact that you could use something called a tree diagram to nicely visualize or organize all of these possibilities, called your sample space. So let's see if we can remember how to do that. I'm going to do a horizontal one. You could also do a vertical one. So I am going to begin by talking about the first event, which is a coin flip. So if I flip a coin, I know that I have 2 outcomes that are possible, if it's a nice fair coin, right? I can either get a heads or I can get a tails, right? So that's my first event. Now it's possible that I then flip a coin again, and then I would do a heads and tails branch from each of these that I just left off of. But it doesn't say that I'm doing it multiple times. It says I'm tossing the coin once, and then I'm also using a fair die to roll. So now let's incorporate the roll of a die. If I roll a die, then after I've gotten the heads, assuming I'm doing them in consecutive order here, let's say I got a heads when I flipped my coin, and now I'm rolling the die, and what are my options? Well, I have 6 options, don't I? 1, 2, 3, 4, 5, 6. And the same thing holds if I got the tails first. I would have 6 possible rolls of my die. Now that's kind of cluttered, so I apologize for the ugliness of it. You can do it in a bigger way on your big landscape paper, or maybe you do it like a family tree vertically, that's fine too. But the whole point is to generate what we call the sample space here. And we're going to use this in our next problem. And so sometimes when you're doing a problem in the homework or on a test, you'll have to first build a sample space and then use that information to answer some probability questions like we're going to see in a second. So let's build it carefully together. The first thing I notice is I could get a heads with any of these 6 rolls of a die. So I could get a heads with a 1 or a heads with a 2. You get the idea, I hope. So H1 through H6. You don't have to write it this way, but I think this is a nice shorthand for doing so. Then you could get a tails with the numbers 1 through 6. Now, if you have your notes, or if you're writing this on paper, which I hope you are when you're doing these questions on your own, perhaps now or later, I would recommend having this written down so that you can then use it for your next question. So this is our sample space. Now, before we head to the next question where we use this information, notice we could have known immediately the number of elements or the number of points in our sample space. We say each possible outcome is a point in the sample space. So the number of points in our sample space, how many are there here? Do you see? How many did we write? Wasn't it 12? That's right. Where could we have gotten that number 12 from? Well, we could have used that fundamental counting principle, right? Multiplying the number of ways that we could get the first event, a fair coin. We could get 2 outcomes, heads or tails, times the number of ways that we could get an outcome for rolling a die, 1 through 6, right? So the number of ways that we can get a coin tossed is 2, times the number of ways that we can roll a die, which is 6, and that's how we could know ahead of time that we needed 12 items or points in the sample space. So even if you didn't do the nice tree diagram like I did above, you could clearly think through, right, heads with this number, tails with this number, all 12 possibilities. So that's also another trick to keep in mind. All right, let's use this information in our next slide. So I'm just going to quickly write that down. Remember what our sample space was. We had heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and then tails 1 through 6. Hopefully yours is less messy than mine. So that was the sample space that we had from question 4. With that in mind, can we answer this question? It says, find the probability that when you, again, roll a die and flip a coin, or in either order, right? Find the probability that you will get a heads for the flip of the coin, and you're rolling a number greater than 3. Heads and a number greater than 3. So let's see if we can find all possibilities where both of those things happen, right? So from these 12 possibilities, how many of them are, let me go back to that slide here. Here we go. How many of them are favorable to us? So how many times do you get a heads paired with a number greater than 3? So greater than 3 would be 4, 5, or 6, wouldn't it? Wouldn't that just be 3 times out of the total 12 possibilities? And then when you reduce 3 out of 12, what do you get? That's right, 1/4, or if you prefer as a percentage, 25%, or as a decimal, 0.25, right? Okay, so now that you saw me do one, see if you can handle the next one. It says find the probability of getting a tails or rolling a 2. Tails or rolling a 2. Now notice here it wasn't and. And was where we looked for both of those things happening together. With or here, remember that means we add, right? So add but subtract if we've overlapped. So let's take a look here. For getting a tails, that was 6 options, right? 6 out of the 12. So that was these 6, okay? What about for rolling a 2? Let me get another color here. How about blue? For rolling a 2, that was a heads 2 and that was a tails 2. So it says or, it doesn't say and, so you don't have to be a tails 2. You could also be a heads 2 and you've satisfied that condition, right? That's what or means. It's more inclusive, right? So we could have a 2 from a heads or a 2 from a tails. So there's 2 of those out of the 12. Now what's the last step we do when we do an or probability problem? You remember? That's right, we subtract if they can both happen together. Can you have a tails, which is also a 2? Yes. And you can see there that we had, in fact, double counted it. That happened 1 time out of the 12 options, which would mean we would just have 6 plus 2 minus 1 as our numerator. In other words, 8 minus 1, or 7 out of 12. 7 out of 12 there. All right. So finally, see if you can do this last one on your own. Put yourself to the test here. It says find the probability that you do not get a heads or that you do get an odd number. That you do not get a heads or that you do get an odd number. So if you do not get a heads, what would that mean? Well, if you do not get a heads, that means that you get a tails, right? So we think, okay, how many ways can I get a tails? There was those 6 possibilities, 6 out of 12. Or means add. And getting an odd number was how many ways? Should be half of them, right? You could get a heads with the 1, tails with the 1, heads with the 3, tails with the 3, heads with the 5, tails with the 5. So that's 6 possibilities as well, 6 out of 12. But with or, what do we have to do as well? So we add, but we also subtract any overlap. So could you get a tails, not heads, right? A tails and an odd number at the same time? Yeah, here's tails with a 1, tails with a 3, and tails with a 5. That happened 3 of the times, 3 out of the 12. So in this situation, 6 plus 6 is 12. 12 minus 3 is 9. So you should be getting a 9 in your numerator and a 12 in your denominator, which hopefully you can reduce because 3 goes into both of these numbers as 3 over 4, or 75%. 75%. All right. So here again, we showed how we used a sample space to then answer questions about probability. Okay. When you're ready, let's head over to question 6. It says a password must have a letter followed by 3 digits marked 0 through 9, followed by another letter. Okay, so what I would recommend at this point, pause the problem, and you can try it on your own first, but if you were following me along here, I would pause the problem and recognize that we are doing one vent right after another, right? We're picking a letter, we're picking a digit, we're picking another digit, and then a letter. So I would write this as the fundamental counting principle, where you're multiplying each number of possibilities together for each choice you make, each selection. So first you're choosing a letter, then you're choosing a digit, followed by another digit, followed by another digit, followed by a letter. Okay. Once you have that set up, that template, if you will, it's just a matter of inserting the correct numbers of possibilities for each selection. So here we notice that we're picking a letter here, and let's see if there's any further instructions. It says, determine the number of possible passwords if, so here comes a condition for us, the first digit, so that would be right here, the first digit, cannot be 0. So instead of 0 through 9, your choices are 1 through 9, right? So that's how many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 opportunities, right? And they also tell us something very important. Repetition is allowed. What does that mean? Well, that means if I used a digit for that first slot, I can repeat it in the second and or the third slot. Okay, so I could use those digits again. And it also means that if I used a letter for the first letter here, I could use it again at the end for my last letter. Okay, so for letters, what am I choosing from? Well, the English alphabet, it's implied, which is A through Z. There's 26 of those. And then for each digit after the first digit, I'm allowed to use 0 through 9 for these two. That would be 10 choices, wouldn't it? Right, because the 0 adds another one. And then for the letter here, again, we're also doing A through Z, which is 26 choices. So now it's just a matter of multiplying those numbers together. And using your technology, you should be able to get the same answer that I did, which was 608,400 different passwords. So these would be the number of passwords that you could create. So if someone tells you, I made the exact same password, what's the probability that they chose the exact same password as you? 1 out of 608,400. So they might not be being super honest unless you have exactly the same things in common, right? Okay, so at this point, we've demonstrated the fundamental counting principle by multiplying the number of ways that you can select each item together. Keeping in mind, if you are allowed to repeat, that number can remain the same, but if you were not allowed to repeat, you would have to reduce your totals each time. When you're ready, let's go to question 7. In question 7, it says, a kitten litter consists of 5 males and 6 females. If one kitten is selected at random, find the odds against the kitten being male. Odds against the kitten being male. Okay, so remember probability and odds. We talked about this at the very beginning of the chapter, okay? We said that to find odds against, you could do it by using a ratio of one fraction over another, right? You could say the probability against, or not in favor, and then you could say the probability for. This is using the language of against and for, but you're welcome to use not in favor and in favor as well. And then you could also just reduce and notice that this just turns out to be the number of ways that are against, and then the colon, the number of ways that are 4. That was our little shortcut, remember? So in this situation, for example, we noticed that if there are 5 males and 6 females, there are 11 altogether. So if I was doing the probability of against getting a male, okay, how many ways can you not get a male? In this case, it would be getting a female, 6 out of 11. And then for the probability of getting 4, I would be saying, how many ways can I get a male? That would be 5 out of 11. And then that complex fraction, remember what happens when the denominators are the same? That's right, they cancel out. You just are left with 6 to 5, okay? But notice that would have been the same thing as my shortcut here. How many ways are against getting a male? Well, the 6 ways that we get a female, right? So 6, 2. How many ways are for getting a male? 5. So the odds against selecting a male kitten here randomly would be 6 to 5, okay? And again, I recommend that shortcut. I think it's a lot faster than stacking the fractions, right? See if you can do the second one on your own. It's kind of clever. It says find the odds in favor of the kitten being female. Well, what did you get? Well, if you follow the same logic here, odds in favor, the shortcut would say how many ways are for your event to how many ways are against your event. So what would this mean? Well, how many ways could I get a female in this situation? 6. And how many ways could I not get a female? That would be those 5 males. So here we have the exact same answer. Now, if that bothered you, I thought they'd be flipped, right? For and against. Notice that I was a little sneaky here. I switched the desired outcome from male to female, and that's why they didn't switch the order. But if I had kept them both as male, then they should have reversed the order. Okay, so that's our quick little review of odds against, odds in favor. Keep in mind here, no more work to do since 6 and 5 don't have any shared factors, but if this had been 6 and 12, you would have reduced. Okay, let's head over to question 8, just 2 more. Ooh, some conditional probability. Here we go. It says the number of cars and SUVs taking the 408, so these are roads near where I live, and I-4 on a certain 10-mile stretch were tracked for 30 minutes as follows. And here's what they found in our table. They found that on I-4, for example, there were 1,500 cars that passed through that location. There were 1,000 SUVs, and then we did the addition for you. Typically, you would do this addition yourself, meaning there were 2,500 vehicles in that time frame that traveled on I-4. Then on the other road, the 408, there were 1,250 cars and 750 SUVs for a total of 2,000 total vehicles on the 408 during that time on that stretch. You could also add vertically, and they did the work for us here, the total number of cars that were either on the I-4 or the 408 on that particular 10-mile stretch, or a particular 10-mile stretch at that certain time, they don't give us the details, sorry, was 2,750. And the total number of SUVs for the same exact parameters was 1,750. When you add up all these figures together, both horizontally and vertically, we should get the same grand total of 4,500 vehicles in discussion here. All right, with that information, now we're just going to practice, can we read a table correctly? That's all we're doing. Now, if one of the vehicles is randomly selected, okay, so from this study, okay, if we're talking about one of these vehicles, what is the likelihood or the probability that it's a car? So based on the study and the information they've given you, can you determine the likelihood that you would randomly select a car from this study? Well, how many cars are there? That's right, 2,750. So we're talking about this number here. And how many total vehicles are there? That's right, 4,500. And you're welcome to do some reducing. A lot of the fancier calculators today will do the reducing for you. You can see that 10 goes into both of them, 2 goes into both of them, 5 goes into both of them, and you can keep reducing and reducing until you no longer can. I believe the final reduced fraction is 11 out of 18, and that's roughly 0.61 or 61% of these vehicles were cars. Okay. Now let's do something a little bit more particular. What's the probability or the likelihood of selecting a car that was in this survey that was on the 408? So it has to be a car on the 408, okay? So how many cars were on the 408? Well, that would just be these 1,250, wouldn't it? So that would be 1,250 out of the total number of vehicles in question, which is 4,500. And again, if we do our reducing, eventually you should come up with 5 out of 18 as a fraction, or roughly 28%. If you change it to a decimal and a percent. All right, now here's the real fun part, in my opinion. We see this symbol here. What is that line, or that line segment? What does that represent? That's right. That's the word given when we're talking about probability. You can look back in your notes or previous videos. And it says here, what is the probability that if you randomly select a vehicle from the study, that it would be an SUV, given the fact that we know it was on the 408? An SUV, given the fact it was on the 408. So where do we begin? Do you remember? That's right. You always begin with your condition. Okay, this is your condition. You know it's on the 408. So the only place you're allowed to look at your chart right now is the column for vehicles that were traveling on the 408 at that time period. Okay, so that would be those 2,000 vehicles in total, and then they have them separated by type. Now it says of those 2,000 vehicles, so that's your denominator, right? So that's where we begin. Of those 2,000 vehicles, which were on the 408, that's where we have to begin, what is the probability that it is an SUV? Well, of those, it looks like there were 750 SUVs. And again, when you reduce 750 over 2,000, you should end up getting the nice little fraction 3/8, or roughly 37.5% exactly, or roughly 38% if you just want to round to something whole. Okay. Finally, can you do the last one now that I did that one for you? Find the probability that you get a car, or a vehicle rather, that is on the 408, given the fact that it has to be a car, right? It's not an SUV. Okay, again, we didn't talk about other vehicles here. So find the probability that your vehicle was on the 408, given the fact you know it was a car. Okay, so where would I have started for this given problem? Yep, that's right, it had to have been a car. And so for the car column, that would be the total 2,750. And being on the 408 from that region, from that column, would have been the 1,250. So having to know where you're looking will save you a lot of time. 1,250 divided by 2,750 should eventually reduce to 5 over 11, or roughly 45%. Okay. All right. So we just did an example of how we could use conditional probability and just regular plain old probability in a table form. The key thing was to notice what was your condition first and only look in that particular column or row, and then figure your numerator out from that. Let's head over to our very last question. Here we go. Question 9. This says a drawer of batteries contains 6 which are defective. I don't know if this ever happens to you. It's either when I'm baking and I go to get eggs and one of them's cracked, or when I go to get batteries for my flashlight during a hurricane, I live in Florida, I end up having batteries that don't work. It's very sad. So let's see if that is the case here. We have a drawer of batteries, and in this drawer of batteries, 6 of them are defective. 14 are working ones. Okay, so it's good, more working than not working. If you were to select 2 batteries at random, find the probability that none of them are working. So this is my scenario. Both of them are not working. Okay, so find the probability that none of them are working. Okay, so keep in mind what we're really tasked to do here. We have a total group of batteries. So let's talk about our total group of batteries. How many are there? 6 plus 14 would be 20. Good. So we know that there are 20 batteries. Of those 20, we know that 6 are what we call defective, and 14 are, they're saying, working or not defective. Okay. So with that in mind, those 2 options, we can now understand the problem, I hope. Okay. So we are asked to take how many batteries from the drawer? Right? How many are we taking? That's right, 2. So we are doing what they're talking about right here. This is called a subgroup. Okay. So we have a group of 20 in the group, so 20 in the group. And we're going to take a subgroup. And sometimes, if you remember from your permutations and combinations section, we remember that a subgroup is kind of like taking a committee, right? Remember when you're forming a committee of people? And you're going to have 2 men and 3 women, or 2 faculty and 3 staff, something like this. Subgroups are when we talk about committees are combinations. The reason they're combinations and not permutations is because the order in which I draw them does not matter, right? If you're going to be on a committee, you're either on it or you're not. That's all you care about. Am I on the committee or am I not? If, on the other hand, you were picking someone to be the president, right, of your organization and someone else to be the treasurer, then the order in which you select them would make a difference if you're picking people out of a hat, okay? But for combinations, you just want to know, are you on the committee or not? Same thing for my batteries. I just want to know, am I defective or am I working, right? So in this situation, we are talking about a combination problem, and it's in particular a probability question. So we have to form a fraction, okay? So for my denominator, that's the easy part. What am I doing? I'm selecting 2 items to be on my committee of batteries, right? my subgroup of batteries. And from how many items? 20, that's right. So from 20, I'm choosing 2. And we had a formula for this, but you could also use technology. That's what we encourage you to do. 20 combination 2, okay? That would be your denominator. And for your numerator, this is where we have to do a little more thinking. We have to actually multiply all the different possible combinations together. So what am I saying? From every category, how many am I choosing? So for example, from the 6 which are defective, how many am I thinking that I'm going to get, right? They said find the probability that none of them are working. That would mean that they are both defective, right? If none of them are working. So we're saying from the 6 defective, I'm asking what is the likelihood that I choose 2 of them? And that means multiply. That's our fundamental counting principle. From the 14 which are working, how many am I asked to choose here? I used the letter D for some reason. I think I said the word defective. That's funny. It's a combination, right? Okay, so 6 combination 2, that gives us the number of ways that we could select 2 defective batteries from the 6 that are in the batch. And now we're going to do 14 combination 0. That gives us the number of ways we can choose 0 of the 14 working batteries. Again, that will just be 1. There's only one way you can choose none of them, okay? But it's important to recognize that by doing it this way, the 6 plus the 14 adds up to 20, and the 2 plus the 0 adds up to 2. You've accounted for every category. The same thing would hold if I was picking randomly from like a cooler of sodas, right? And I want to know how many of the Diet Peppers did I choose and how many of the Coca-Colas did I choose. I would then, the same thing, I would say how many Diet Peppers were there total and how many did I take out? Same thing. Okay, so when I do the math here, using technology or using the formula that you learned, you're going to get 15 when you do 6 combination 2. You only have one way to choose nothing, so that's going to be 14 combination 0 is 1. And then there are 190 ways that you can choose 2 items from 20, okay? And again, this is the formula for combinations. Look in your notes in the previous videos, or you could use technology, okay? And when you reduce 15 out of 190, you get 3 out of 38, or roughly 8%. Well, that's good news. That means I have roughly a 92% chance that this does not happen to me, that I get at least one that's working. Okay. All right, so we reviewed quite a lot of questions that you might see on a future test. So the main thing you want to do is organize your formulas and really practice so you can differentiate which formula to use in which case. Make sure you're also comfortable using your particular calculator or technology that you are going to use on a test. If you have any questions, feel free to reach out to me. But in the meantime, happy practicing, because math is not a spectator sport. I'll see you next time.